Thank you, Emmanuel and Anshu, for this great introduction and for actually inviting me to give this keynote at the 5th COLOC workshop at Europar in 21. Unfortunately, we are still in a virtual setting, but I'm very positive that by next year we can probably go back to a more normal interaction. So I'll be giving this talk over video here. So first, I'm going to talk about a project that has been going on in my lab since quite a long time, actually, nearly 6 years at this point. It started to be funded by, it was initially funded, by an ERC starting grant, and I'm glad that actually I just recently received an ERC consolidator grant to continue the project. So this is a quite long-standing project, and there are many people involved. So on the technical lead side, Tal Ben-Nun, and then many students, Alexandros, Johannes, Tiziano, Timo, Andreas, Manuel, Philip, Dominic, and a whole lot of other people in the DAP team that are to be credited. During this talk, I will present a whole lot of different results and different papers and from different sources, and you will always find the references at the bottom. If you have any questions during the talk, please hold them back, because we won't actually have any time for questions in this relatively short session. But there will be a panel at the end of this workshop where I will be very happy to answer all the questions that you may have. So let's get started right away. And let's get started with the dark slide. So the dark slide, not to say the dark side, is actually telling you something that you probably know because you're at a workshop that worries about data locality and about data movement, optimization, all kinds of these things. So we kind of can just repeat this over and over again, and I want to keep it very short. Communication dominates arithmetic. That's actually not even my slide. That is a slide I borrowed from NVIDIA. And you can see on this slide quite massively how various distances you travel on chips. So this is a chip that's just 20 millimeters by 20 millimeters approximately. And that chip, you take about 20 picojoule for a 64-bit double precision floating point operation, but then just moving 256 bits a little bit across the chip is already more than this, and actually moving it across half the chip is significantly more. Accessing in DRAM, in SRAM is more, accessing in DRAM is more, sending it further is even larger. So in terms of energy consumption. So this is something we have to deal with. This is just getting worse over time. Because there are various laws that when we shrink the chips, or not the chips, but the process technology further, the metal layers will actually get thinner, and thinner metal layers have a larger resistance. So, but I'm assuming you're well aware of this in this workshop, so let me not spend too much time on this. But one thing I actually wanted to point out here is that since a while people have been looking at how to deal with these problems. And there's a wonderful summary of a series of workshops, the PADL workshops, which were held by, mostly organized by Didem and Anshu and John, and I contributed a little bit myself too. And after the series of workshops, Didem and Anshu coordinated a wonderful summary paper of all the results that we have gathered with this large number of people that you can see there about what happened in the past about data locality abstractions in the HPC context. But now the question is, based on this knowledge, well, how do we take those ideas and move them forward into productive performance computing? Because at the end, it's not just about high performance, but these days it's also about high productivity, especially in contexts of cloud computing and the newer generation of national labs. So the second question I would like to pose to you then is, what is actually the fastest growing user base to adopt GPUs even faster than traditional high performance computing? So I'll give you about 10 seconds to think about this. And in 10 seconds, you will, of course, come up with Bitcoin. But Bitcoin is not the right answer because the programmer base is quite small. But you can see the correlation between the stock, the market value of a Bitcoin coin and the stock value of NVIDIA is quite strongly correlated until here, where it starts to be decorrelated because Bitcoin goes down. NVIDIA goes up, and you can look at the time. That's about 2019, July 2019. So what happened in July 2019 that is not Bitcoin? So I'll give you about 10 seconds to think about this. Well, it happened before, but it was actually really taking off in about 2019. Well, that is deep learning. Everybody and his dog now runs deep learning systems. It's running on my cell phone. It's probably soon going to run on my watch. And everybody knows PyTorch and TensorFlow. It is as famous as probably the most famous programming frameworks for a restricted domain. And these two, they support you in writing code for for deep learning systems, essentially. There are some, they go a little bit further, more general machine learning systems, but the vast majority of the code written in PyTorch and TensorFlow is for deep learning systems, and all of that basis on Python. So Python is a highly productive language, and Python actually was really not invented for computational and data sciences. However, NumPy was invented for that purpose. And NumPy is a very significant subset of Python. If you're a computational or a data scientist, you definitely know NumPy, because that is the Python way to program arrays. Of course, everything in data science and computational science bases on arrays as a data structure. And that's quite important. So many of these frameworks have been developed to actually support and accelerate NumPy and Python in general, but many of those actually aim at NumPy. But how do we now compare these frameworks? And this is the first part of my talk. Well, we need a benchmark. Like we have the NAS parallel benchmark that were written in Fortran at the very beginning, then later extended to C, and that's where they stopped. They were covering a large part of the application domain. And what we're proposing another benchmark that we call NumPy bench that incorporates many pieces of applications, of real application kernels, really like the NAS parallel benchmark, but written in NumPy, much more productive and in only tens of lines of code. And here we actually have a quite large number of kernels, 51 kernels from 9 different domains, implemented, and you can use them to evaluate your Python framework. And of course, the evaluation is with respect to performance, but also with respect to productivity. So that was a new aspect that was added to a NumPy bench, which didn't really exist in the NAS parallel benchmarks. And then, of course, there are multiple frameworks like the NumPy framework itself, Python, Numba, CuPy, and our own framework, DACE, that I want to talk about today. But we will be using NumPy bench, specifically a subset of NumPy bench that is Polybench, for most of the evaluations today. Right? So when I talk about performance. And now you can look at NumPy bench results over various frameworks. Like I don't have enough time to go through all of this, but we have a NumPy baseline. We have Python, Numba, DACE GPU, and CuPy GPU speedups, and you could now look for each of those 51 benchmarks, how they perform. You can see some of those are not. Like green is good, high speed up, red is negative speed up, so slow down. You can see some don't really perform well on GPUs. DACE actually refuses to compile most of the ones that don't perform well on GPUs, and so this is there's of course something to improve. But on average, if you just look at the totals summarized by domain, or maybe even summarized by absolute total, you can see these various speedups, and these frameworks are actually helping. So DACE is the strongest framework for this particular set of benchmarks. And now the question is, how do we get there? How does this work? And this is where we get to the COLOC workshop. It's all about the data movement. And I want to use the remaining 18 minutes to explain you a little bit more how we achieve this. Not so much how we parse the language. Python is a different topic, but how do we achieve these optimizations in order to make it fast on specific target devices like on parallel CPUs, clusters, and GPUs, of course. And then there's even a little bit of spatial programming if you're a fan of FPGAs, because all of those are supported. But going a little bit deeper into data-centric Python, what does this really mean? Well, it means that you write Python code, but more specifically, you write NumPy code. Like you can see here, there's a function, something else. There's an example program that is just annotated as a DACE program, so it's quite simple to do this, and it's basically normal NumPy. One difference is here that we have to annotate the types, which is just hygiene in Python code, I would say today. So these are type hints that we actually require for DACE. Then you just write normal NumPy code. And what the framework does, it takes this imperative code and translates it to a parametric data flow representation where it's not imperative anymore, where it's the data flow code. And you can see this here on the right. That's actually just a screenshot from our tool. It translates it into these funny looking graphs that I will explain in a couple of minutes. But each of those lines, basically, you can see here, each of those statements turns into one of those blue boxes with a lot of internal structure, because these statements are non-trivial. If I say A plus A, you can see A is an array of 20 by 20, so that's a matrix addition here. That is another matrix addition, and then there is actually matrix multiplication down here, which we implement as a so-called library node, and I will talk about this a little bit more. But what we see for each of these statements, we have certain input arrays, in this case B and A, and output arrays, in this case the return array, which is made up essentially because that's a logical name for whatever is returned from the DACE program. Okay, so this is really how it works, but how does the vision actually work? And I think you got it by now. We have a domain scientist who works at a very abstract level, at the DSL level, NumPy, TensorFlow, PyTorch, MATLAB, some high-level DSL. Then we have an applied scientist who translates this, so this is us in this case. And then we have performance engineers, and this would be you again, who works on this internal representation, the Dataflow representation, to make it more amenable to specific target devices. And then we just have a code gen. So a code gen is really just spitting out GPU code, CPU code, CPU code, GPU code, and FPGA code at the end in terms of C++ code generation. So that's basically just a pretty printer for source code. And then, of course, the programmer, the domain scientist, only works with tens of lines of code. If you have actually looked at PyTorch or TensorFlow, you can define deep neural networks in tens of lines of code, and they're extremely powerful. Where does the performance come from? That is really from rewriting this internal representation, this graph, but the rewriting is not manual. The rewriting is done in an automatic way where we specify the rewrite rules in code, and those are reusable across different programs, across different codes, different graphs. And at the end, the code generator is typically thousands or even tens of thousands of lines auto-generated code, which you do not necessarily want to look at, or you do not definitely don't want to write yourself, because there's all this loop unrolling and really using all intrinsics and whatnot that you may not know and may not want to know. So let's dive a little bit more into detail what it means to what our view, the data flow, the data-centric view really means. So here we have an equation that you would translate into code. But actually, we don't worry about that equation in our representation. We just worry about the data flow. Here you see the equation consumes a variable x and produces a variable y. And actually, we don't, as I said, what this computation does, we don't care. So now we call these inputs and outputs memlets. In the following, you will see this a little bit more. And of course, these memlets are typically arrays, because otherwise the code would be very fast if it would just be scalar. So they can be usually a very large arrays. And then you process this in parallel with lots of different processors and different iteration spaces. So this is kind of the general view. And of course, this graph is relatively hard to look at. So what we do is we have a shortcut way, and this is what you've seen before. This is what we call the burger. It has an opening as kind of a scope. So it has an opening statement that defines the iteration space. What is the source of this array? Where does the data flow here into this tasklet in the middle? And then it closes the iteration space down here again, and it produces an output range in B from 0 to n. So we can now take this, and actually we can define multiple different states. So this is kind of like a state machine where if you have a part of your code that is not representable as pure data flow, you can actually introduce these two different states, state 0 and state 1, and define a dependency edge between those, an artificial ordering in addition to just the data flow ordering. Of course, we don't necessarily want this. We want the largest possible regions of code expressed in data flow, but it's not always possible. Sometimes we need these states. And now we can have a quick tour across these different nodes that we have in these graphs, because everything we do is kind of graphical programming. Because fundamentally, in order to understand data flow, it's hard to look at source code. You really want to see a graphical representation where your code, where your data flows, and how to map it to a target device. So we have these states that I just mentioned, we have these tasklets, but we never actually really look at the content of the tasklet. But of course, we need to remember the source code of the tasklet, that later in the code generation phase, we can actually generate that correct code. We have arrays, which are extremely important as sources or sinks for data flow. We have now these different maps, which are really iteration spaces, and they're independent iteration spaces. Whenever you have loop carry dependencies, you express this either through data flow or through different states. Here you see an example of a more complex graph, and you can see all these symbols in this graph. So furthermore, we have nested SDFGs, which is basically a tasklet that is an SDFG itself. So think of it as a function call, which can be arbitrarily complex again, but we usually inline these things then because it's guaranteed to be inlineable in our case, so we don't have recursion, at least not infinite recursion, to enable this mode. We have streams for FPGAs or spatial devices. We have ways to map to streams, so again, specialized iteration spaces, and we have conflict resolutions, which now gets a little bit more into detail, where we have resolve conflicting writes to the same variable. We could specify this as a sum or as a subtraction or whatever operation you want, actually. And then we have these library nodes that I mentioned earlier, where we can use optimized libraries. For example, here the gem library that is extremely important. So we can even plug in your pre-optimized assembly code or vendor-optimized libraries like BLAS or cuDNN or any of these libraries, because that's super important. So this is now the programmer view. You see here a screenshot of Visual Studio Code where this is fully integrated. You can see the SDFG here in the middle. You can see lots of handles. On the very left side there are transformations, and here we see how this transformation is just applied. This map was just split into two by just clicking a set of predefined transformations. Of course, they're not just predefined. You can actually write these transformations yourself. And these, we have a library of transformations that we have written, but you can write arbitrary additional transformations. You can apply them, and you see immediately the impact it has on the graph, and you see immediately the data flow. Over here in this area, you see the properties of each of these nodes. I know this is relatively fast, but you can just try it at home. And here you see the Python source code. So you can edit all of this live. You can edit the Python source code live. It's going to regenerate the graph. It's going to regenerate the possible transformations, because we check, of course, if they're applicable, and it's going to show you all these nice things on the right side. So this is how the performance engineer interacts with the graph, how the performance engineer really extracts performance from it. Then you can actually go a little bit more into detail here, and for each of those elements in the graph, you can see the actual data flow. As you can see, you hover over a tasklet, it tells you the computational complexity. Here, flops. How many flops are in there? You hover over an edge, it tells me what is the data flow, what is the data volume that is moving. It can tell you symbolically, but it can also tell you for a specific setting. So here we just initialize these symbols, KMNL to 32, 32, 64, and here you see actually computed that the flow volume here is 1. Of course, it's in the iteration space, and here the volume is K times M times N. So this is quite convenient. So furthermore, we have full debugging support, so you can set breakpoints in your Python source code and jump to the generated C code. Right, so if you want. So you can go arbitrarily deep to debug the framework itself, or to debug your codes, and how you can look at the code that is generated and maybe even design better transformations and better code generation. So this is how it works. Days is an extremely versatile platform. So far we have various front ends, NumPy, DaysML, C, grid tools, Fortran in planning. We have lots of backends, NVIDIA GPUs, AMD GPUs, x86, ARM, Intel, Xilinx FPGAs. Soon we will have an RTL backend, and it's relatively easy to extend. So you can write your favorite DSL, and you can also write your favorite code generation backend, as long as it fits somehow in the C or C++ language specification. So now I want to give you some examples in the remaining 8 minutes, what we did with it. And as I mentioned, each of those examples is basically a full paper, so I will only have 1 or 2 minutes per example, but you can find it at the bottom left, the reference of the paper, if you're interested, on our YouTube channel of my lab, the Scalable Parallel Computing Lab, which is you find up here. You will actually find videos explaining every single paper with the respective author of the paper. So I'll just give you a rough overview. So here we use these Polybench examples, and this is quite interesting. When we're mapping NumPy to CPUs, the key principle is we keep the data flow of the vectorization around and use it for the mapping to the target device. So to illustrate this a little bit more, we have this Polybench, which is designed by it's a relatively old benchmark from the polyhedral community, which is very, very useful, and we ported it to Python, was partially ported to Python, or to NumPy, and we fully ported to NumPy, so it's fully part of NumPy Bench. The nice piece here is that now a Polybench actually contains C code. And now you may think, well, Python is really slow, so Polybench C will be much faster. But as you can see here, for GCC and ICC, both auto-parallelization, we get significantly worse performance than actually from NumPy itself, because NumPy is using libraries to optimize this code. And if you keep the vectorization, and then Days even speeds up 10x on average over NumPy, and of course much, much faster over the C versions in this case, which is quite interesting. So for me, that was quite surprising that with Python, I can actually beat somewhat optimized C versions of these codes. That's quite an interesting result. And we even outperform CuPy in most cases on the same target GPU, just based on the transformations we are doing. Okay, but this is micro benchmarking, but let's go a little bit further to real stencils that are used in the weather and climate area. Well, let's start with something we can actually compare to other researchers. And here's a wonderful paper that manually tuned spatial and temporal blocking using OpenCL on FPGAs. So this is a manually tuned paper. It uses relatively simple stencils. So there are 2 stencils, Jacobi 2D and 3D, and diffusion 2D and 3D. And the upshot of our result is just that with this automatic tuning and this, of course, this code that we generate is not really manually writable in some sense, because it's thousands of lines of code with complex annotations. So we achieve 23 to 44% better performance than the manually tuned code, because of course humans are limited in code generation capabilities. But now let's look a little bit more into real stencils. You can see this stencil up here. That's actually a horizontal diffusion stencil extracted from a real weather code on real FPGAs. Now we cannot compare to others, but we can compare to a CPU. I mean, other people did not run. We were the first ones to run the stencil code on an FPGA. And we compare it to optimized versions on a CPU, the P100 and the V100. And we see we are actually slightly slower, but mainly because all these codes are memory bound and the FPGA has a really bad memory subsystem. At least it had at the time. Now we have HBM FPGAs. If we run the Stratix 10, assuming we have infinite memory bandwidth, so just reading trash data, we can achieve a higher performance than a P100 and actually relatively close to a V100, which is about the same generation in terms of silicon process. So we see that we get an extremely high utilization, 48% DSP and 300 megahertz. So that's actually quite good for these for this particular FPGA. But unfortunately, it's suffering from insufficient bandwidth. So FPGAs are a good target. We can more or less automatically map to them. But unfortunately, the architecture needs to change. So same on GPUs. If we map deep learning workloads to GPUs now, so that's another front end of DACE. It's actually a front end that injects directly from PyTorch, then translates to this intermediate data-centric representation through the Onyx representation, and we achieve again similarly high performance that you can just look at yourself, and you can look at the paper that's going to appear very soon. But they're quite impressive performance results for single kernels, where you can see here from 1500 to 500 something. And then for full networks, like efficient net here, we achieve a couple of % speed up against highly tuned frameworks. Actually, data movement is all you need. It was one of the best papers at MLSys 2020, really pointing out, again, the theme of the COLOC workshop. Data movement is the most important piece here. So we can also map C and C++ codes, in this case Lulesh, automatically, so not just Python, to CPUs, and we get 21% faster on a multi-core CPU. So now let's, as one of the last examples, if we are mapping NumPy to large-scale CPU clusters, here we are comparing to, so by the way, let me just elaborate a little bit more on this Lulesh. This is a manually tuned, again, OpenMP version by the authors of the benchmark that we compare favorably against with 21% higher performance. Here we compare to Dask and a Leagate prototype by NVIDIA, and we can look at lots of these plots here, where we have multiple different lines. So the parallel efficiency on the left, so the triangles are parallel efficiency. Let's look at just at the absolute runtime. These are the circles. So we have the Dask runtime in blue, the DACE runtime in red, and the Leagate runtime in green. And you can see that the DACE runtime is the fastest here. Leagate with numbers of processes here times 18, essentially. The Leagate runtime is extremely good compared to Dask, at least, which actually you can see here, until it runs out of memory. And unfortunately, Leagate in this prototype version crashes with several different errors for large-scale runs, but we believe this is fixed by now. We reported it back to the Leagate team, so don't overemphasize these crashes. Look at the performance. And then we have lots of different results here. As I mentioned, this whole NumPy bench has lots of different applications, and we can now look through all of those, but the gist of these graphs is always the same, and we are really using an MPI-like interface through these library nodes. Again, like we can call optimized gem libraries from DACE, but we can also just call optimized MPI implementations, which is very useful, of course. So then the highlight of our DACE story is essentially the 2019 Gordon Bell Prize, where we ran on the top one machine at the time, Oak Ridge Summit supercomputer, with more than 21,000 GPUs. We achieved a speed up of more than 10x, or a capability improvement of more than 10x compared to a previous Gordon Bell finalist and honorable mention code, using these data-centric principles. And then again, if you care about the details, there are lots of talks that you can find on our YouTube channel online. But again, the same principle, just looking at data movement and optimizing it, in this case communication, that we were able to reduce by more than a factor of 100 times by just looking at rearranging the data layout in these graphs. And this is quite impressive. So we are working on multiple things, multiple avenues to continue this. So let me just wrap up the talk now. So I talked about the motivation. So why do we want fast Python code? Why do we want to run this on high performance computers? Because it's productive. And really, it is inspired by TensorFlow and PyTorch and the success in deep learning. And this is, but we started actually before the success came, but they completely passed us. Of course, that community is very, very large. Here are the principles. I would like to encourage you to actually look at it, install it, look at the GitHub source code, contribute to the source code. And if you really like it, then you should join our group and apply for a PhD or postdoc position to work on DACE or other things we have in the group. So then I talked about how it works in practice. I talked about the programming framework. And at the end, I presented several use cases, including the Gordon Bell Award in SC 19 or in 2019. So with that, I would like to end my talk. And again, if you have any questions, I will be at the end of the workshop, or not at the end, but in the last session of the workshop on the panel that we can discuss these questions, and I'm very happy to take them there. Thank you very much.